dear students. Welcome to Nuclear Physics 1 lecture number 16. I'm Dr. Pervez Ahmad. In this lecture, we will start the discussions on the alpha particles. So the content of the lectures are, we will have a brief introduction of the alpha particle first. Then we will move towards alpha decay. We will discuss that how alpha decay occur. That is how alpha particle they are being produced during a particular decay process that we call alpha decay. Then we will discuss that why classical theory failed to explain the alpha decay, or we will try to explain that why classically it is impossible for the alpha particle to decay or to escape from a nucleus. And then we will derive a sample expressions for the kinetic energy of alpha particle. So let's proceed towards today's lecture, that is the first part, that is alpha particle. So what is alpha particle? Alpha particle is the same as the helium nucleus. That is, it contains two protons and two neutrons. With two proton and two neutron, it has a mass equal to 4, and it has a double positive charge because of the two protons, and because of its heavy mass and a double positive charge, the alpha particle has lowest penetrating power. The example of the alpha decay is the decay of radium to radon. So you can see here, radium has atomic mass equal to 226, with the number of proton 88 and number of neutron 138. When it decayed to radon, so radon has the atomic mass 222 with the number of proton 86 and the number of neutron 136. So just like we mentioned, that with the alpha decay, the mass number is reduced by 4, just like you can see it here, the difference in the atomic mass of radon and the radium, and the atomic number is reduced by 2 just by the reduction of the two protons. So here you can see the atomic number difference between the radon and the radium. So how the process basically occur, how the alpha particle occur, what is the theory of the alpha particle decay, or that in short we can write alpha decay. So we have to develop a theory. So for that we consider a radioactive nucleus that we denote by the capital X with a subscript Z, that for the atomic number, and the superscript A for the atomic mass, and that we call the parent nucleus or the parent nuclei, and it has a mass that we denote with the capital M, and in bracket we write this particular parent nuclei. So this is the mass of uh, the parent nuclei. We have a parent nuclei which we denoted like this, and the mass of the parent nuclei is denoted by capital M, but in bracket we have that particular parent nuclei. So what happened after then? Two or more product can be produced and the decay. We have this parent nuclei, and this parent nuclei has the mass which we denote by M, and inside the bracket we put that parent nuclei. So we say that when the decay process occur, so during the decay we have two or more product that can be predicted as the result of the decay. So let the two just like we mentioned, we can expect two or more than two product in the decay process. So let the lighter one be denoted by M with the subscript Y, and the mass of the heavier one that we call daughter nuclei be denoted by MD. So these are the two nuclei that we are expecting to be emitted during the decay process. So the conservation of the energy, then we can write for such a process as the mass of the parent nuclei is equal to um, the mass of the daughter nuclei plus the mass of the lighter nuclei plus the energy, or the energy that's been released during the decay process, or we can say that the difference in mass which been evolved as the energy during the decay process. So this is a simple relation for the conservation of energy during the decay process. So what is mean Q here in this particular reactions, the conservation of energy reactions here. Q is the energy release. I mean that we call disintegration energy, where we say that the mass difference, the mass difference between the parent and the daughter nuclei uh, is converted into energy. So that's why we call this Q as the disintegration energy, and it's equal to the kinetic energy of the reaction product. I mean, this Q is equal to this is called the disintegration energy and equal to the kinetic energy of the reaction product. So here we have something special for this Q, that is the disintegration energy. You should remember that if the value of Q is greater than 0, so what it would mean? It would mean that a nuclide is a nuclide is unbound, unstable, and may decay. I mean, on the basis of this Q, we can predict the conditions for the parent nuclei. So the first condition is that if we have, the reactions and in which the Q value is greater than 0, so a nuclide will be unbound, unstable, and may decay. But at the same time, if we have the condition that the Q value, that is the disintegration energy, is smaller than 0, so decay emitting nucleus do not occur. Decay from the emitting nucleus will not occur. That is, the decay process will not occur. So that's why we call this as disintegration energy. And for the decay process, the value of this should be greater than 0. Otherwise, the decaying of the emitting particles from a parent nucleus that will not occur. So let's do that for the alpha particles. Just like we mentioned that alpha particle is basically a helium nucleus. So the nucleus has a binding energy of 28.3 mega electron volt. I mean, we can do that. Very simply. We can do the calculations very simply, and we already know that it's a well-known fact that alpha particle has a binding energy of 28.3 mega electron volt. So if the last two protons and two neutrons in a nucleus are bound by less than 28.3 mega electron volt, then the emission of alpha particles that we call alpha decay is possible. So what it means? Let me repeat it again. Uh, we have the nucleus, that is helium nucleus alpha particle, and it has a binding energy of 28.3 mega electron volt. I mean, this much of binding energy is needed to hold two proton and two neutron in the form of alpha particles. So now you should need to understand, if the two protons and two neutron in a nucleus are bound by less than 28.3 mega electron volt, then the emission of alpha particle is possible. That is, this much of energy is required to hold two neutron and two proton in the form of alpha particle inside a particular nucleus. I mean, if the energy is less than this amount, so the alpha particles may not stay inside the nucleus and it will emit from the nucleus. That is, the emissions of the alpha particle from the nucleus is possible. So we have the relations in this case when we have the emission of alpha particles from a parent nucleus. So we have the expressions. This is the parent nucleus. So we say when the alpha decay occur, so the mass of the alpha particle will be reduced by 4, and the atomic number will be reduced by 2 with the alpha emissions. So the same we can write for the Q values. That is, we have the mass of the parent nuclei minus the mass of the daughter nuclei and minus the mass of the alpha particles whole multiplied by c square, that is the speed of light. So against the same conditions, if q is greater than 0, so alpha decay is possible. I mean, if the value of q, that is the disintegrations value, if it is greater than 0, so then alpha decay is possible. And an example we consider that of uranium 230 with the alpha decay. I mean, when alpha decay occurs from uranium 230, so it's converting into thorium with a mass 226 and atomic number 90. So the appropriate masses for these reactions, for this reaction is, I mean, uranium 230 has a mass, I mean the exact mass equal to 230.0333927 atomic mass unit. The mass for the alpha particle is equal to 4.002603 atomic mass unit, and that for the thorium is equal to 226.02489 atomic mass units. So by inserting these value into the formula which we have here, uh, so you just need to put the values here for all these elements. So you will get, I mean, here we just put the values and we get the value, I mean we get the mathematical value for the q, that is the disintegration energy, and this is equal to 6 mega electron volt. So now what it mean now, in order for the alpha decay to occur, two neutrons and two protons group together within the nucleus prior to decay, and the alpha particle has difficulty in overcoming the nuclear attractions from the remaining nucleons to escape. So now that the energy is less than that is being needed for the alpha particles, but here is a problem inside the nucleus. That is, inside the nucleus we have other particle as well, and those particle also has attractions on the alpha particle, that is on the protons and the neutron. So this is why we're saying that in order for the alpha particle for the alpha decay to occur, two neutron and two protons group together within the nucleus prior to decay, and the alpha particle has difficulty in overcoming a nuclear attraction from the remaining nucleon to escape. So this is the potential energy diagrams of the alpha particles. So here we say that uh, the alpha particle, the calculation that we did in case of decaying of uranium 230 to thorium, it has an energy of 6 mega electron volt, and this is the barrier energy. The barrier energy, I think, is greater than 20 mega electron volt. So now what is the possibility? Is it possible classically, I mean, for the alpha particle to overcome these barriers, or what otherwise can be the possibility? So let's discuss it here. So the barrier height that you can see the here is greater than 20 mega electron volt. So what we can have now, the kinetic energy of the alpha particle emitted from the nuclei range from 4 to 10 mega electron volt. So the barrier height is greater than 20 mega electron volt, and the alpha particles that is emitted, it has a kinetic energies which lies in the range of 4 to 10 mega electron volt. So what it means, so classically it is impossible for the alpha particles to reach the nucleus, but the alpha particles are able to tunnel through the barriers. So this is something, I mean, we're lying between the classicals and quantum. So classically, I mean, if you look at the barrier, so it's impossible for the alpha particle to reach the nucleus, but the alpha particles are able to tunnel through the barriers. I mean, this is the barriers, so the energy is less than that's been required to overcome these barriers. But quantum mechanically, we say that there is a possibility that the particle may tunnel through these barriers. So, and also you can see here, uh, we have the energy levels, that is E1 and E2. So a high, this is a higher energy, E2 is a higher energy as compared to E1. So a high energy E2 has much higher probability than does a lower energy E1, that's for particles to overcome the barriers. So there is a correlations between lower energies and uh, greater difficulty of escaping, that is a longer time. I mean, uh, the energy, the greater the energy, the more will be the possibility for the particle to escape. And the same applies for the lower energy. We have the lower energy, so we will have the lowest possibility for the particle to escape from the nuclear barrier. So these are the classical things. I mean, classically, it's impossible for the particle to escape from the nuclear barrier. So now, I mean, we mentioned that quantum mechanically is possible, so that the particle can penetrate through the barriers. It can enter, or it can escape from the nucleus. So that quantum mechanically, that we will discuss in the coming lectures. We will draft the expressions for that. Now, classically, or we can say that we should derive a simple expressions for the kinetic energy of the alpha particles. But for that, we assume a situations. We assume a parent nucleus, and that parent nucleus we assume initially at rest. So the total momentum is 0. The final momentum of the daughters that we denoted by PD, and the alpha particle that we denoted by PA. PA has the same magnitude and the opposite directions that you can see it here. The parent nucleus, and after the decay, the daughter nuclei and the alpha particle, they are accelerated in the opposite directions with their own momentum. So from the conservation of energy and conservation of linear momentum, uh, we can determine a unique energy for the alpha particle. That is, you know that q value is equal to the kinetic energy of the alpha particle plus the kinetic energy of the daughter particles. So we also mentioned that the kinetic energy of the alpha particles, I mean both the alpha particle and the daughter nuclei, they have the same momentum but in opposite directions. So we can say that alpha particles momentum is equal to the daughter particles momentum. So we can write the relation like this. I mean, just put out the values of kinetic energy of alpha particles, so we get these relations. So here we just need to put the values for the momentum of the daughter particle, which is equal to p square over 2md. This is the momentum of the uh, this is basically the expression for the kinetic energy of the daughter nucleus. So here we mentioned that it is equal to the momentum of the alpha particle as well. So that's why here we put the expression for the kinetic energy and term of momentum for the alpha particles. So we just simplify the expressions. We do a sample mathematics. We do the simplifications. So here we get these relations, and further simplify by for getting the value of k alpha. So we get k alpha is equal to a mass of the daughter nuclei divided by mass of daughter nuclei plus alpha nuclei whole multiply by q. So here you know that mass of the daughter nuclei, we say it's 4 less than the mass of the parent nuclei. So here we can write a minus 4. A minus 4 mean the mass of the daughter nuclei, which should be 4 less than that of the parent nuclei. And what about the mass of the daughter nuclei plus mass of the alpha particle? So as a total, this is equal to the atomic mass of the parent nuclei, which simply we can write by A, and this whole multiply by Q. So this is the expressions for the kinetic energy of the uh, alpha particle. So it's a sample expression for the kinetic energy of the alpha particle, and we can call that as the classical expression for the kinetic energy of the alpha particle. That is, the kinetic energy of the alpha particle is simply equal to uh, mass of the daughter nuclei divided by the mass of the parent nuclei, whole multiplied by the disintegrations energy. So that's all we have for this lecture. Thanks for watching, but stay tuned for the next lecture. That will be lecture and because in that lecture we will have a discussions on the uh, quantum theory of alpha decay. So stay tuned with that lecture. Till then, bye bye.